In this tutorial we will do the model of an elastic plate foundation. First of all, we create the boundaries of the model. Let it be 8 by 6 meters for this example, and I also create some irregularity in the corner by deleting these two lines, and then I can define the domain itself, which will be a plate with a thickness of 200 millimeters, and the material will be 20 megapascals concrete according to the NBC standard. Then I can check the render view if it looks like as we wished, and then I continue with defining the nodes for the columns which are connecting to this plate. These columns are supposed to be here, so I can move on and define the surface support, which will be a Winkler spring type elastic support for this domain, and the value will be twice as much as the default value, and it's defined. So as for the load cases, we first create a dead load case, then the live load, which will be consisting of live load 1 and live load 2, and we have a snow load, and these are arranged into the same load groups with the same name. First of all, I define the dead load for all these columns. We have, let's say, 40 kilonewtons, and the plate itself shall be calculated by the software. I also assume some wall connecting to this plate, so a linearly distributed load will be modeled here. I can draw any pattern I'd like. Now I have this load as well. Live load 1 will be assumed to be acting on these two columns with 100 kilonewtons. Live load 2 will be on these two columns with the same intensity. Snow load is assumed to be transferred by the columns with 15 kilonewtons. So we create the load combinations, which will be the ultimate load combinations for this example, and we can check how many combinations are generated by the software. These are according to the NBC 2010 standard. So I create the mesh, which will be a rectangular mesh. I can modify some parameters here to get a nice mesh, but for this specific example it's quite simple. So I can run the calculation and check the first result, which will be the envelope of all the load combinations of settlements. So this result includes all the load combinations, and this is the minimum settlement. This is shown as a colored diagram, but I can check this type of diagram as well, showing the elastic settlements of this foundation plate. So the next result we are interested in is the reinforcing design moments. This shall be viewed as a two-dimensional isosurface, and to understand the results we have to show the relative coordinate system of the domain, because the first result is the reinforcement design moment about the local y direction. The local y direction is this yellow coordinate. So these moments which are shown at the moment, they are the moments about this y-axis, and it's the maximum envelope values for these results. In the same direction we have the negative design moment envelope, and of course we have these two for the other direction as well. I can check any result I want if I move the cursor on the specific point on the mesh. Even interpolated values can be immediately asked by moving the cursor within the finite element. So as for the reaction force, I can check it on a three-dimensional load result as well, and it can be seen that the maximum reaction force is about 60 kilopascals. So this shall be the basis for ground pressure capacity. That's all. Thank you for watching.